Dr. Tugrul for your talk on new steps in clean energy technologies and business concepts. Our next speaker is Dr. Tugrul Ozel. He is currently an associate professor in Industrial and Systems Engineering Department in Rutgers University. He is the director of Manufacturing and Automation Research Lab at Rutgers. He has over 20 years of experience in the fields of manufacturing research. His research focuses on computational modeling and optimization of advanced manufacturing processes and development of innovative micro-nano devices, processes, and integrated systems. He published 2 edited books, 1 patent, over 100 articles in leading journals and conferences. He is the editor-in-chief of International Journal of Mechatronics and Manufacturing Systems. He is senior member of Society of Manufacturing Engineers and associate member of SERB International Academy of Production Engineers. He received his BS degree in aeronautical engineering from Istanbul Technical University in 1987 and PhD degree from Ohio State University in 1998. Please welcome Dr. Tugrul Ozel.
Thank you, Yiğit. Thank you very much. İlk önce biraz Türkçe bir şeyler söylemek istiyorum. Her şeyden önce Rutgers Üniversitesi Endüstri Mühendisliği bölümünde 2002 yılından beri çalışıyorum. Çok değerli, çok başarılı production ve manufacturing sistemleri konusunda değerli hocamız Tayfur Altok'un yarın 2. ölüm yıl dönümü. Kendisini hiç beklemediğimiz bir şekilde genç yaşta kaybettik. O yüzden çok duyguluyum şu an. Bu arada onu da anmak istiyorum. Kendisi Türk komünitelerinde çok etkin çalışmalarda bulunmuş bir insan. ODTÜ mezunu olduğu halde her türlü Türk eğitim kurumundan gelmiş kişilerle çalışmış birisi. Ben İstanbul Teknik Üniversitesi 1983 yılında girdim. 1987 yılında bitirdim. İTÜ Uçak Mühendisliği bölümünden mezunum. İTÜ Uçak ve Uzay Bilimleri Fakültesi'nin ilk mezunuyuz jenerasyon olarak. Ardından doktoramı Ohio State Üniversitesi 1998 yılında bitirdikten sonra akademisyen olmak istedim. Dolayısıyla sizlere akademisyenlikle ilgili mentörlük yapmak çok isterim. O yüzden kendi araştırmalarımı anlatırken içerisindeki araştırma fokusunu, araştırma yoğunluğunu özetlerken bu bağlamda düşünmenizi istiyorum. Akademisyenlik, özellikle üniversitelerde çalışmak sadece ders vermek değil, aslında araştırmacılık, inovasyon ve bununla birlikte yeni buluşlar, yeni bilgiler geliştirme özelliği. Özellikle teknik üniversitelerin, uygulamalı araştırmalar yapan üniversitelerin buna şiddetle ihtiyacı var. Dolayısıyla bu konuda tüm İTÜ mezunlarına, İTÜ öğrencilerine ve meslektaşlarıma bu konuda faydalı olmak isterim. Size bazı yaptığımız araştırmalarla ilgili çalışmalar göstermek istiyorum. Belki bu konulara yönelirseniz, bu konulara ilginiz olursa neler var, neler mevcut diye görebilirsiniz. Konuşmamın bundan sonraki bölümünde İngilizce devam edeceğim. Arada böyle Türkçe bir şeyler söylemeye çalışacağım. Mümkün mertebe. So, in our research group, we focus on advanced and innovative manufacturing systems. Advanced manufacturing technology is a very broad area, but we are focusing on manufacturing, especially multi-scale, nano-manufacturing, micro-manufacturing, and manufacturing at a scale comparable to us. So that includes aerospace and military equipment components, energy devices, fuel cells, solar panels, batteries, medical devices, implants, microfluidics, microneedles, and specifically we work on developing new processes, understanding processes, developing process models, especially computational models, so that the physics and fundamental science-based understanding of those processes can be generated. So the processes that we are focusing are micro nanomaterial removal processes, laser micromachining and processing, and additive manufacturing, also known as 3D printing. In addition to those activities, we do manufacturing automation, which is a traditional trust area in manufacturing systems. It includes flexible manufacturing systems, advanced machining systems, and computational modeling, and also advanced tools and coatings. So just to give you an idea about manufacturing in multi-scale, is essentially we produce products today that are much smaller than we used to produce traditionally for certain reasons. For example, there is a high demand in miniaturization of devices. Parallel to that, there are new materials developed, for example, nanomaterials, nanotechnology, biotechnology, constantly producing new materials. So the applications of those micro nanoscale are very, very broad in aerospace engineering, automotive, biomedical, electronics, energy industries. Just to give you some idea, I'm not going to go all the specifics, I don't want to bore you, but microfluidics devices are very, very interesting devices that the healthcare cost can be reduced, and fighting against diseases can actually be stronger. Other devices include microturbines, coronary stents, dental implants, and microneedles, for example, all require miniaturization. So in our laboratory, we focused on developing new manufacturing processes and production processes in fabrication of products to serve for those purposes. Just to give you some examples, we have laser micromachining setup, we have microbinning setup, and then we have laser-assisted microbinning setup, and all the features you see here can be produced with such processes, and then we do computational modeling, essentially go to the fundamental science of those processes and understand those processes. And I will skip some of the slides because I have quite many. I don't want to get into too much of the details. Microfluidics can be a one trust area, which microfluidic channels can be machined by using laser micromachining, for example. In this, you can utilize various kinds of polymers available, and some of the polymers are actually very soft polymers, which provide flexible systems, microfluidic systems. So we do modeling of the laser micromachining processes. We use light, laser, light physics in order to develop computational models in support of our experimental analysis. And then those are, for example, some of the results we obtain, machining microfluidic channels, and then we construct some models to be able to predict that. So in the computational environment, you can actually design the process for various materials. Another interesting area that we're focusing is the additive manufacturing, 3D printing. 3D printing has been out there for a long time. So just recently, industrial 3D printing, industrial additive manufacturing is becoming a reality. So we took a role in order to study selective laser sintering, selective laser melting. Again, our focus is to develop computational models to design the process and understand, improve the process performance, the related manufacturing systems. So materials, obviously there are various kinds of materials. We focus on materials that are useful for aerospace industries and biomedical industries, you know, nickel alloys, nickel-based alloys, titanium alloys, and others. Another, just to kind of give an mention, innovation aspects of our research, we focused on developing with micro-machining processes, prototypes that can be used in order to produce, in order to generate a new product in especially healthcare delivery systems. So microneedles as a concept is an alternative to hypodermic needles, in which that you don't have a sharp, long metal piece, is a needle going into the skin. There are tiny little needles in an array that is fabricated on a polymer, and the polymer also has the necessary drug in it. So Rutgers technology is patented, and we have a patent of developing those microneedles out of polymers, 2 different polymers that we tried, and then there are some other competing technologies from the other universities. So as a result, we developed an innovative manufacturing process and a product, an integrated system that will allow us to, fabricate those very small microneedles. So this is the development stage. We started out with the computer design, and then we developed the process. We fabricated some different prototypes, and they are ready to be tested in the, some drug delivery systems, for example. And here are some example images of those fabricated microneedles. And in addition to that, we explored new processes to fabricate this, because when it goes to mass scale manufacturing, we should actually reduce the cost of manufacturing. One of them is 3D printing. So these are the 3D printed prototypes of the microneedles. And again, this is useful for timely release of drugs, not given a drug, and it could be useful for fighting against diseases such as malaria, and you can actually apply to yourself, self-applicable applications. So we're currently seeking some industrial partners to start business in this area. Another group of activity we do is manufacturing automation, and as I mentioned to you before, in which we focus on traditional manufacturing systems and how we can model and optimize and generate automation strategies. And in my department, this is a traditional strength, and we call this automation altogether. And in my group, particularly in this flexible manufacturing systems, we try to develop computational models that would actually mimic the actual process and improve the process automation. So here is a chip removal process or metal cutting process in which we develop and validate experiments, and then we try to understand the resultant product attributes such as surface integrity, structural integrity, part quality, etc. So these are some representative images. And in these, actually, we have a lot of activities that 2 of the PhD students finished their work. The first PhD student worked on this, as you can see from the papers, Karpat, Yiğit Karpat. He is now an associate professor, just recently promoted in Bilkent University Industrial Engineering Department. Another PhD student worked on this, finished. Tugrul Ozel has finished last year. He is a postdoc in Clemson University. Yiğit Karpat has studied, for example, hard turning. In this process is a green environmental friendly process because it eliminates use of using lubricants, so it's a dry, environmentally clean manufacturing process. So we developed process simulations again, and then provided process improvements. And at the time, we also developed some new tool geometries we call microgeometry, and optimize the tool geometry to improve and also optimize the process performance. And we are continuing to that effort in order to generate more computational models to predict the microstructure, especially microstructure components that are important in fabricating aerospace parts. And then we can specifically predict temperatures in a very small scale and quite accurately, which is very difficult to measure. So another project that we are working on is machining titanium alloys, and in which we're actually looking at the process modeling again. We use advanced material models, computational constitutive material models, and then we developed chip formation simulations using finite element method. From this, we actually can predict the temperatures during the machining, and then optimize the process performance. Another activity, we're focusing on micromilling of titanium alloys. Micromilling titanium alloys can produce, for example, dental parts, bridges and crowns and implants. And in the future, they're thinking about having micromilling machines work on your dental operations, automated. So the process knowledge is very important in that respect. We have micromilling experiments and then micromilling finite element modeling. And as a result, we can understand the process model. And I think we have a movie here, or hopefully it works, but it didn't. Then we can predict process outputs such as forces and temperatures and strain on coated and uncoated tools, and from which we can generate some knowledge which is applicable to optimize the process. And as a last item on that is 3D finite element simulation modeling, and you can see those are computation models very large. It takes a very long time to run them. Finally, the last project I'm going to talk about is essentially machining induced residual stresses and surface integrity on aerospace alloys. So you can see that aircraft engine has lots of aerospace alloys, titanium and nickel alloys, and they are mission critical components. Their life cycle is very important. And then we look at processing of those materials in order to make the final products, and in which we understand the residual stresses. And we conduct experiments. From the experiments, we measure residual stresses, and from this, we develop finite element simulation models and measure residual stresses in the part. Then we try to develop optimization schemes and look at what is the most desirable machining or manufacturing process parameter set in order to find an optimum set of solutions. So we use a lot of computational methods in order to do that. One of the methods we use is the particle swarm optimization, for example. So as a result, working in a university as an academician requires doing a lot of research. I just wanted to show you, run through many research projects. Obviously, they are too technical for this audience and also maybe our audience over internet. However, you can see that if you're interested in pursuing careers in manufacturing systems area, these are possibilities. And then we worked over the years with National Science Foundation. Here are the 4 grants that we obtained from them. And we work with the biomedical product design and development with the European Commission Research Directorate project. And also we work with many companies, United Technologies, Timken, Weiler, Conicity, and others in order to conduct our research. So as a result, if you want to become an academician in the university, this is a very nice, beautiful career, a very enjoyable. You get to work with many, many wonderful people, teaching, research, and going to the conferences, and advising, editorialship, writing books. I love my job, and I recommend that to anybody if they want to pursue a career in academia. Thank you very much.